going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. Maybe this is hard to see. There we go. All right. Today we're doing deriving equations practice using kinematics. Deriving equations is a skill that the College Board asks us to do over and over and over again using different contexts. But what you'll see is that as long as we follow our mathematical steps, draw our picture, list our variables, figure out our knowns and unknowns, and then select the appropriate equation to use, we will still be able to solve this. It's just without numbers. Deriving an equation is solving a math problem without using numbers. And so that's a skill we have, and it's a skill we need to practice for our AP test come May. Here is our problem. It's at the end of your packet if you want to follow along. If not, I have it here for us. So we launch a projectile at a speed of this at an upward angle of theta. Let's start my picture. I've got an angle theta. It has an initial velocity, it says, of v0. At an angle of theta, I'm already starting my picture, okay? An angle, the projectile is launched and lands at the key same height. So if I'm launching it from here, it's going to travel over here and land at the same height. Derive an equation for the time the projectile is in the air in terms of speed, theta, and g. Well, let's go ahead. I know that this is moving in 2 dimensions, so let's go ahead and set up our equations. That's delta x. Let's go vx. Let's go, I know time is always between the two. Tx equals ty, simultaneous but independent. Acceleration, the x is 0. Change in y, I know that's 0 meters. Because I'm launched and I land at the same height. So what is the change in y? Well, I start here, it goes up and comes right back down. That change in y is 0. I've got an initial y velocity equal to, I don't know. I've got a final y velocity, which is equal to the opposite of the initial y velocity, because if I'm launched upward and I land at the same height, symmetry rules tell me that I'm going to have the same velocity, just downward. I know the acceleration in the y direction is baby g, or it's 9.8 meters per second squared downward. We'll figure out if we want to use positive or negative for that later. Displacement, velocity, acceleration, time. I'm good. That's everything I got there. Okay, so derive an equation. It says for the time that it's in the air. Well, time in the air is going to be ty. It's an appropriate thing to think about. How high will it go? How far will it come back down? What's time? All right, so let's figure that out. So in order to do that, let's pick an equation that includes velocity, acceleration, and time. And if I get out my equation sheet and I look at my nifty physics manual and I try to find the equation that says my velocity and time equation, it's the first one. I have my v final equals v initial plus at. This is my physics equation. How do I know I'm using this one? Because again, I'm looking for time, and it says in terms of velocity and acceleration. So I pick an equation that has those things. Notice, it doesn't talk about distance. I shouldn't be using distance or displacement here, so I pick this equation. Now, to derive an equation in this context, I start to plug in information from the problem to kind of like specify or make this equation more specific. So, the initial velocity, well, I'm operating in only the y dimension. So, what is the initial y velocity? Because v0 is initial speed. The initial y velocity is my opposite side. So the sine theta of my angle is equal to, so katoa, initial y over v0. What is the initial velocity in the y direction equal to? Well, I do my algebra. Speed times sine theta is equal to my initial y velocity. So I've got this. If I'm talking, this is final, this is this, right? Okay, well, this goes here. Okay, got it. I can substitute that in. Over here, what I know from this is that my final y velocity is exactly opposite of that because of symmetry. So what's my final? Negative v0 sine theta goes right there. Perfect, I have that. Instead of acceleration, what's acceleration in the y direction? Acceleration is g, because it's in free fall. So let's go ahead and start making this a little different. I've got negative speed sine theta is equal to speed sine theta plus g times t. I'm going to get rid of some of this stuff now, get rid of a little bit of my picture so I can keep doing my algebra. Let's, subtract speed times sine theta from both sides. we end up with negative 2 speed sine theta is equal to g times t. Divide both sides by g, and I end up with negative 2 initial speed sine theta over g is equal to t. And you're asking yourself, why is it negative? That's a little strange. Should it be negative? And the answer is, yeah, because what is the direction of acceleration? G is pointed which way? Downward. Initial speed is pointed which way? Well, upward. So I've got my upward and my downward. So in order for time to be positive, this is going to be negative because speed is positive. Baby g in this case is going to be downward and negative when I plug that value in. So negative 2v sine. It's weird to call time negative, so time will be a positive number, but this, based on my direction, is my equation. Does this equation make any sense? Not really. Is it useful? Not entirely, but I did solve this problem for the time it's going to take for the ball to launch and reach the same height in terms of speed and acceleration and theta. That was the goal. Derive an equation for the time the projectile is in the air in terms of those variables. Done. I did it. I picked an equation, I drew a picture, figured out my variables, picked an equation, plugged those variables into that equation, and then isolated the variable. Let's try a different one, all right? So I've got one. Now I know that the time it takes to go here to here is that. Now it says derive an equation for the range of the projectile. Well, that's delta x. Now I'm trying to find the range of the projectile. So how do I do that? Well, I know when I'm moving in the x direction or the x dimension that it's only moving with a constant velocity. So there's only one equation to really use. And that's my change in x is equal to the initial velocity times time plus 1/2 the acceleration times time squared. But we all know because there's no force acting in the horizontal dimension or x dimension that that's 0. So we're left with x displacement or range is equal to the x velocity times time. All right, so do I know the x velocity? No. But can I go back and look at my original picture? Yes. I go back here and I say, well, this is my x velocity. It's the adjacent side. I would say that my x velocity, or x, is equal to the speed time, not sine anymore because I'm using the adjacent side, cosine of my angle. Okay, or I could, I'm skipping steps. I say this, right? Cosine theta equals adjacent over hypotenuse. Multiply both sides by v0. I end up with v0, or speed cosine theta is vx. Sorry, I'm jumping ahead. I apologize. In order to find this, let's go ahead and say delta x is equal to speed cosine theta times time. And I'm like, I'm done. I solved it. I found vx. I'm done. But it says derive an equation for the range of the projectile in terms of speed, theta, and g. And you ask yourself, well, shucks, my equation has got time in it. What do I do? My equation's not done because I haven't met the rules of the problem. It says I'm only allowed to have terms that are speed, theta, and g, and I have t. If only somewhere I had solved for time using v, theta, and g. Oh, nah, right? So I'm going to go ahead and take this. I've already done it, right? I've solved for time above in terms of v, or speed, theta, and g. I can make a quick substitution. So instead of this time, I will substitute in negative 2 speed sine theta over g. And now what am I left with? Holy smokes, let's just like distribute the snot out of this thing. And we're left with these. I'm going to combine some like terms. I'm going to see this is negative 2 cosine theta sine theta, because those are just two things. And I don't know, there might be some trig identity I'm not picking up or I'm not remembering from my like calc days. I don't know, but I would think about that. I've got two speed terms, so that's going to be v0 squared, all divided by baby g. If there's a way to simplify that, I'm okay if you do that. I'm not mad if you don't. And this is going to be equal to the range of the object. Do I have an equation for a range? Yup. Is it in terms of speed, theta, and g? Well, I got theta, I got speed, I got g. I got rid of time, so that's good. This equation does match the rules of the problem. It only contains terms that are outlined in the problem. This is how I would derive the equation. Again, I drew my picture. I organized my variables. I then picked a general equation. You pick the general one off the equation sheet, the owner's manual, and you start to make it specific to your problem. We looked at the picture. Instead of using Vx, we use V cosine. Instead of using t, we use the time derived from above. This is how we derive an expression, okay? We have one more problem at the bottom. It says, using your equation, explain why 30 degrees and 60 degrees will shoot the same range. This is not a deriving question, but it is a way for me to use to show my understanding of the equation that I produce. So basically what we're looking for here is this. Ask yourself, if cosine of 30 degrees times sine of 30 degrees, is that the same? Is that equal to or different than cosine of 60 degrees times sine of 60 degrees? I'm not going to look at my equation because this isn't going to change based on the angle. That's not going to change based on the angle. My speed isn't going to change based on the angle. But what you'll find is that the combination of these two things, they're always going to be the product of those two things, the multiplication, the answer to that will always be the same. So launching something at 45 degrees, launching something at 45 degrees maximizes the range. But if you're 15 degrees below that at 30 or 15 degrees above that at 60, you're going to end up with the same range. Now, they'll be in the air for different amounts of time, but they will end up landing at the same spot. And that's kind of the point this last problem is trying to make. All right? Folks, the whole point of this is so you understand deriving equations is not scary. It is the exact same process we would solve if there were numbers. It's just solving a math problem without numbers, which can be scary. If you got questions, drop in the comments, send me an email, ask me in class. Till next time.